Good morning, class. Today is the second lecture on heat transfer, where in the last class we have introduced what are the heat exchanger, we have defined various applications also, and we have defined the types of flow in that lecture, and we also discussed the overall heat transfer coefficient, the Fouling factor. Now, in this lecture, uh, in the last lecture, we have also derived one expression, that is that Q is equal to UA of delta Tm. Now, in this lecture, we will able to understand how we can calculate the mean temperature difference in case of parallel flow, in case of your counter flow, and how we can use those relation to solve the numerical based upon across flow heat exchangers. What we are doing today is we have to derive an expression for the mean temperature difference for parallel flow heat exchanger. Now let me show in a figure. Let's say this is a kind of a arrangement in a heat exchanger where here is the TH temperature, that is the hot side inflow, and here is the cold side temperature, and here is the outlet at the hot side, and here is the outlet at the cold side, right? So the flow takes place in this direction, makes it a parallel flow. So this is the inlet temperature, so let's call this as THI and this as TCI. Now here, this is the mass flow rate of the hot side, and this is the mass flow rate at the cold side. Now to drive an expression in this case, what we have to take certain assumptions which will able to solve that the mean temperature in this case. What are those assumptions? Let us say assumptions. Number one, that heat exchange is insulated. Which means there is no heat loss to surroundings, which means heat exchange is between the hot fluid and the cold fluid only. This is my first assumption, right? Second assumption in this is that the potential energy and kinetic energy changes are negligible. Number three, the fluid specific heat are constant. The number four, overall heat transfer coefficient is a constant. And let me show you the temperature profile in this case. Here is the temperature which is at THI, and here is the temperature which is at TCI, right? And on this side, the THI, there will be a decrease in temperature because the heat is being transferred from hot fluid to the cold fluid, right? So here is a temperature drop in the hot side. Same as in the cold side, there will be a temperature gain in this case, right? So in the parallel flow, the temperature profile looks like this, where this difference we call this as delta Ti, and on this side this difference we call as delta Te, right? Let me show you. It is delta Te. Now let us take a small area here to analyze this kind of a flow, right? So if this is the x direction, let us call this as dx, and this is the complete length of the heat exchanger, right? So the area in this case, that small differential area, will be b times of dx, right? Now if we consider an elementary area dA, which is nothing but b times x, where b is the width of the heat exchanger. So this is a two-dimensional figure. So if we extend this, then this thing is the b. Got it? Now as you know that small change in heat is given by the relation U A of delta T. Now in this case, we have to calculate what should be the value of delta T in case of parallel flow heat exchangers. And you also know that, let me mark this as 1. You also know that is dq will be mCp of delta T, right? So if we call for hot side, it will be minus of m specific heat at the hot side of dTh. Similarly, we can call it as dq is mCpc of dTc. Now let me show you in the figure. Now at this point and this point, the difference is dTh, and at this point, to the entrance of the elementary area and to the exit of the elementary area, this is dTc, that is the change in cold side. Whereas if you see, the hot side is decreasing in the temperature, and whereas Tc having the increase in the temperature. So heat is being exchanged between these two fluids. And why this is negative? because the heat is decreasing in the positive side, right? Now if you see again, this delta T is called as local temperature difference between hot side and cold side, right? So let me start. So we can write it as, that is d of delta T, the rate of change, we can call it as dTh minus dTc. Because why? Because delta T is nothing but it is the net local difference between hot side and the cold side. Now if you put the values of dTh as, it is minus of dq by mh cph, again minus of dtc is what? If you take this, then it is dq by cpc, right? And this is nothing but, and if you take dq out of this, you will get minus dq is out. You can write this as 1 upon mhcph plus 1 upon mccpc. Got it? And if you put dq value, which is ua of delta t, and a is what? B dx. So I can write it as dth is nothing but minus u b dx, that is ua, again delta t, again the bracket starts, I'll write it as, it is mh cph plus mc cpc. Now on, if we take delta t on this side, we can write it as d delta t upon delta t, and which is constant, that is u is constant, right? B is constant, then these terms are also constant as per assumption. So we left with your dx, right? And if I take integration, let me show you. If I take the integration of this, so it will be delta t I by delta t e. Okay, so it is delta ti upon integration. So we will have d delta t upon delta t, which is equal to minus 1 by mh cph plus 1 by mc cpc. U is constant, b is constant, so we have the integration from 0 to L of this dx, right? So where this delta ti is nothing but it is the difference on the inlet side, and delta t is the exit temperature difference of both the fluids, right? So upon integration of d delta t upon delta t, will get what? Will get log of delta t e upon delta t I. Got it? And on this side I'll get MHCpH plus MCCpC UB. Again on integration of this I'll get L minus 0, right? So on this side I'll get B into L, which is volume, B into L, which is area, right? And we can also write this in terms of I can write this as delta TH minus delta TE upon Q plus I can write this as delta T, that is Q of U into area, which is ln of delta TE upon delta TI. Right? Now similarly I get Q out, and if I take this, I'll club this with this term and I club this term with this term, so you'll see you'll getting this difference, right? So I can write it as ln, which is I'll get minus and this is what, again delta Ti and delta Te, right? So I can write it as, that is Q is nothing but it is minus of UA of delta Ti minus delta Te upon ln of delta Te upon delta Ti. And if I have to remove this negative sign, I can replace this as UA of delta Ti minus delta Te upon ln of delta Ti upon delta Te, which is Q in this case, and this is the performance equation for parallel flow heat exchanger, right? So if you compare this with your old equation, which is when we start as delta Tm, so you can clearly see that delta Tm is nothing but it is delta Ti minus delta Te upon logarithmic of delta Ti upon delta T E. So why this is in the term of log? So this mean temperature difference is also called as LMTD. Somehow in papers generally ask drive an expression for LMTD in case of parallel, which means logarithmic mean temperature difference. Got it? So this is your governing equation in case of parallel flow heat exchanger. In the next lecture, we'll do the derivation for the counter flow heat exchanger. So here we have started this from this. I revise it with the 1 minute. We have taken these assumptions. This is the diagram, right? The temperature drops on the hot side is like this, cold side is like this. We have taken the small differential area, which is B times dx. Then we started the derivation with this equation, that is Q is delta, that is UA of delta T, where delta T is the local temperature difference between the hot side fluid and the cold side fluid. We also know that the dq is mcp delta T. So from there we have written the two equations for hot side and the cold side, right? And then we'll put the difference of the hot side and cold side, and then mathematically we solved a relation which comes to be this. Thank you.